The plan for this morning is that we will continue where we left off yesterday and have a little bit of a think about how we can make the problem significantly more difficult, and so we start to sort of break things. So as a very, very brief reminder, this is what we want to do. We want to take 5, or well, M in general, actuators and stabilize the flat film solution of Navier-Stokes. And we like to do it with these feedback controls, which realistically we can only compute for systems of linear ODEs, or in very, very special cases, some linear PDEs, but not the sort of ones we're worried about here. And so we followed a similar method to Susana with KS, and we showed that if we have full observations of the interface, skip forwards, full observations of the interface, we can, here we go, there we go, for this huge region of the parameter space, control towards the stable flat solution, which is really nice. But as Susana mentioned earlier, it's very unrealistic to have full observations of the height and the flux, or even full observations of just the height and then approximate the flux. And so what we'd like to do essentially is relax the requirement that either the matrix C or the operator C, sort of whichever frame that we're sort of thinking in, is the identity, right? And so we've got two methods that we can use to do this, one of which we've sort of hinted at before with that system of equations, and the other of which is something slightly different. It's called the Leuenberger observer. And so, so yesterday we had a think about how we can solve the continuous algebraic Riccati equation. But the problem is if we keep C being some general operator, then this is what we end up with instead, is this sort of system of coupled equations. You'll recall that this top one looks like the Riccati equation, the second one is this Lyapunov equation, and this third one is, it just sort of closes the system. And yesterday we talked about how we can do some clever numerics to solve the algebraic Riccati equation, and I'm not going to go into detail about clever numerics to solve this one, because there isn't a huge amount of clever numerics that we can do. There was this paper quite recently, actually, which sort of tells you how difficult this problem is, because this is a really classical problem in control, and it's only very recently that we've got good converging algorithms for finding this thing. And so essentially we have to do an iterative procedure to find these matrices, which is sad because it takes forever, because solving the Lyapunov equation, which is the sort of limiting step, is quite slow. But the nice thing about this paper is that they proved sufficient and necessary conditions for the convergence to be successful. And the problem is that the most difficult of those is that the initial guess for this matrix K that we want to find must stabilize the problem. It doesn't have to be optimal. So essentially all the iterative procedure really does is make an already functional gain matrix more optimal with every iteration. And finding a stabilizing matrix at the start is a very difficult problem. But you take it, on word that we can solve this problem as long as we can find a good initial guess. And so this is what happens if we plug that in, right? So now instead of observing the entire interface and then, doing a correlation with this gain function, we only observe at a finite number of points, and then we somehow use that information, that's what this gain matrix is capturing, to decide how big these controls are going to be. And we can no longer look at a row of the gain matrix to look at some physical understanding. This is a little bit more sort of black box. But you can see for this example here, for a sort of moderately high Reynolds number, 5 observers and 5 controls does work. And we shouldn't be too surprised about this, because again, earlier when Susana was talking about just Navier-Stokes and sort of picking control policies with simple proportional controls, that was able to function, right? If you had a control and you just set it to be proportional, then that worked. And this should be a slightly better version of that, right? Because that would be like setting K to be the identity matrix, which might be a relatively good guess, and often it is stabilizing, but not always, and that's a bit part of the problem. But you can see here that just as before, we managed to damp out these perturbations, and unsurprisingly, it's a bit slower than it was before, but it still manages to work, which is quite nice. And so this diagram here is a little bit of a mess, but I haven't managed to think of a better way to present it. And it essentially has the same Reynolds axis along here, and then we've got the number of controls and the number of observers, right? So what you'd expect is that, like we saw yesterday, larger Reynolds numbers mean that those sort of inertial effects are more important and the problem is more difficult, especially because as the Reynolds number increases, the weighted residual model becomes less accurate. And you should also expect as the number of controls increase, we should do better. And as the number of observers increases, we do better. Because after all, if we let the number of observers go to the number of discretization points, then essentially we're in exactly the same regime as we were before. And we know we can control that. Unfortunately, you can see with all these red crosses, this is where we didn't manage to find an initial stabilizing guess. And so we didn't even manage to find a matrix to test, which is a real shame. But you can even see for lower values where these white dots are instead of the black dots. The white dots are where we failed to stabilize the Navier-Stokes interface, even though we found a matrix that said it would stabilize the linear system. And so what's happened here is that the nonlinearities are too big and the system is too different to the one that we've designed the control policy for. This isn't, I'm almost less surprised by this than I was by the plot that we saw yesterday, where we managed to control everything everywhere. Yes?
In these cases where you can stabilize, if you got an initial condition that's close to a line, would you be able to? Or nonlinear
That's not something we've looked at, because with all of these we controlled from the most nonlinear wave, or we also did some tests with random initial perturbations to double check that it's not some special case with the travelling wave that we can control towards the flat solution. But I would imagine that if you controlled from a very small perturbation at very small times, when the wave was very small and fairly linear, then it would probably work. But that's not actually something we tried. You'd expect it to work, though, I think. But yeah, like I said, the real problem with this method is it's unreliable to even find the matrix itself, let alone try doing the control. Okay, so that's that one. And again, this is using pretty classical control techniques. Again, with exactly the same process as yesterday, which is sort of chopping up the Navier-Stokes and making lots of simplifications so that we can squash it into a system where these techniques are going to work. Okay, but if we think about a simpler problem, right? Imagine we just had some sort of, like a PDE that just had a traveling wave, like the transport equation or something like that, right? And we only had one observation of the interface and we have a periodic solution. Well, after the wave has traveled one period, actually we've observed the entire interface. And so it's silly to discard all of the past information. And in this case, it's a little more problematic because we've not just got a traveling wave in general, so we can't perfectly observe the system from a finite number of observers. But there's definitely a huge amount of information that we're discarding if we just observe at a finite number of points. And we should be able to take advantage of that information rather than just forgetting about it. And so this isn't going to be a sort of pure feedback control, it's going to be something slightly different. And this is what's known as a Leuenberger observer, is where we build up, in parallel to observing the system, we build up sort of the information that we've got and we try and sort of retain that. So if we recall this sort of unstable subsystem that we had earlier in Fourier space, what we really want, all we really care about, like Susana mentioned yesterday, is the values of these unstable modes that we're trying to control, because they're the ones that are difficult, and the stable modes, they're the very short wave ones, they're just going to damp themselves out. But we don't know what that is. If we knew, then we wouldn't have this problem. And so let's have some estimator, right? Let's say we know approximately what they are, and now we just need to figure out how we can best work out what this estimator is, right? And so what we're going to do is allow Z to evolve in time, and there are two parts to this. If we just look at this part, we're saying, well, Z, let's allow it to evolve with the linear dynamics, because that's what we'd expect. And we could do this with nonlinear dynamics, but then we wouldn't be able to work out this quite so nicely, and this would be a lot more expensive to compute, right? Because what we don't want is to end up with some very expensive observer where we are now having to solve some complicated PDE all of the time, because that discards all of the gains you get from these nice feedback controls, which are so simple to compute. And so what we're going to do is add a forcing term here, right? And so you can see this term in the brackets, we observe the true interface, and then we observe the approximation. So we take our estimations of these unstable modes, we transform them back into real space, and then we sort of fake observe them. And so if the estimator exactly matches the observations, then this term is 0, and we just allow things to keep going. And otherwise, we've got some non-zero forcing term. And we just need to decide what does this operator L look like. So if we plug in, if we sort of try and work out the dynamics of the error, so that's the unstable mode subtracted with the estimator, and we sort of plug in various things and, you know, put in the equation for this in here, and that there's a corresponding one for the stable dynamics, and add in this one as well, then lots of nice things cancel out, and this is what we're ending up with. And this term here, we don't really care too much about what all of these things are. They're just linear operators. These are stable, and so we know they're going to decay. So don't worry about this term. And so therefore what we need to do is choose this operator L, which is the thing that we have control over. We need to choose this so that this matrix has all negative real parts of the eigenvalues. And that should sound very familiar to you from yesterday, because that's just a pole placement or LQR or whatever. We've already done that. But we need to take the transpose first, but you know, the maths is exactly the same. So that's really good news. We know how to do this because we did it yesterday several times. And this one's even better because actually this matrix is very small, right? If we're only thinking about the unstable modes, then maybe this has only got 5, 10 elements in it. And so we can actually use the sort of default MATLAB LQR type things or pole placement because they're going to work. Okay, so just like before, we've got a sort of a number of different Reynolds numbers, so more difficult at the bottom. And at t equals 0, we'll turn on the controls. And there's a sort of little spoiler on the right-hand side about what's going to happen. But you can see that immediately the top one sort of goes too quickly, but you can see we've got this estimator which is tracking relatively well the height of the largest perturbation, which is what we want to get rid of. And you can see that over time we are getting nice decays in terms of these perturbations, which is good. And again, just like before for large Reynolds numbers, you can see that both the estimator and the solution aren't really doing anything useful. This estimator, the linear dynamics aren't doing much. It's just being forced by that forcing term. Every time it passes over an observer, it just pushes up another wave, and that's how the dynamics are really happening. Okay, so we go back to one of these diagrams, and we can see that actually we don't have any of these red crosses anymore, which is really nice. We've just got successful control, and you can see actually earlier, so you pointed out that, well, for these smaller ones that were failing, maybe for smaller linear waves they would work. Actually, this one manages to control those. It's a lot less sort of fragile, both numerically and on a sort of from a control perspective, which is quite nice, because all of the matrices that we're having to compute for this are very small. And that's one of the biggest problems with the output feedback problem, is that you're doing lots and lots of numerics on very large matrices with, you know, things that are approximating Dirac delta functions, and so they're very sort of numerically unstable. And this avoids all of those problems, which is nice. But unfortunately, you notice that, you know, we no longer have access to these high Reynolds number, well, high for thin films at least, high Reynolds number regimes, right? We can't do control here anymore. And that's unfortunate, but this is now because we're not only needing the thin films to be like-weighted residuals for the control, but we also need it for the estimator. And so the sort of combination of the two, it starts to break down here now if you have thicker films or more viscous films or whatever. Less viscous. Yeah, less viscous. Right, that's all I've got to say about thin films and making our control problem slightly more difficult. And you can see we sort of managed to make it break, and it would be nice to see if there's anything we can do about this. But thank you very much, and I'll hand back over to Susana for the rest of the model predictor control section.
All right, so you get me back. And as I said yesterday, like the rest of today is going to be trying to push the problem to a case where linear controls will not work. So we're basically thinking about, well, it was a thin films problem we could think of that was hard enough, the hardest liquid film problem that we could think that was still a liquid film, but then wouldn't work with the linear controls that we talked about yesterday. So we're going to do something a bit different today. So the idea today is we're going to look at other control mechanisms, and we tried some other things that I'll talk a bit about before I show you the problem that we'll look at. And then what I'll actually use as a controlling mechanism is going to be electric fields, which again, Dimitrios talked a bit about 2 days ago already. And then I'll explain quickly why linear controls won't work in this case, and then tell you about what we're doing instead, which is optimal control. So I've already done some optimal control when I was showing you LQR, but that was still all for systems of ODEs, and today we're going to do a PDE, constrained optimal control problem. And then I'll show you some of our results, and then do the same thing that I did yesterday, which is let's try and do the controls for the models directly into the NS. Unsurprisingly, it's not going to work, and then I'll show you what we're doing instead, which is called model predictive control. Okay, so as I sort of hinted yesterday already, when I managed to make the controls work for the Kuramotsi-Washinsky equation, I was all excited, and then people said, no, you have to do better, and then we went to the thin films, the long wave equations, like the Benny and weight residuals, and we were all very happy, like it works now, this is a model you trust, go and do experiments for us. And then the people who were doing the experiments were like, oh, we can't actually go and drill a hole in our very expensive experiment equipment, you have to do something different. And what they suggested at the time was that we used heating. So in these plates, apparently it's very easy that you put some copper wires there, and copper heats and cools very quickly. And so they were like, if you can design a control like that with a localized heating, then we're going to be happy to try and make that work. And so we went and we did the models, and then everyone flew to a different country, and we stopped working on that. But there is a model that we believe it will work for heating, although we did try some proportional control, like what I showed you yesterday, and that worked very locally, because if you think about how heating works, if you're heating at the surface and you want it to influence the interface, the heat has to travel from the plate to the interface. It takes some time, it diffuses, and so the effect that it has is very, it's much less direct than what we've seen. And so we paused the temperature control problem for I don't know how many years it has been now. One day I'll go back to it. But now what we're looking at is electric fields. So this is the problem I'm going to consider for the rest of today. So we still have a thin layer of fluid on the plane, but to make it harder, we make it go under, so that, you know, by itself it will already try to fall, and you want it to stop it from dripping. And to control it, or even to model it, we're going to assume that there's like a wall on the other side, which is a perfect dielectric, and where we can impose an electric field with voltage phi d of x of space and time, and the liquid is a perfect conductor. Now I don't know a lot about electrohydrodynamics. You'll have to ask somebody else. Adu might know a bit more than I do. But yeah, so the problem is very simple, but now your forcing term comes from this electric field. So this is the thing that I can control. And Dimitrios already talked a bit about this a couple of days ago. So if you apply constant electric field, this is always destabilizing. But we can try and make this vary in space and time, and see what happens to it. Okay. So this is what I just said. So we try to vary the electric field in such a way that the interfacial stresses do their thing, and we try to stabilize the interface either to flat or to something else. Okay, so the problem, like for this problem, we started directly with the weighted residuals model, because we knew that with this we had hopes of controlling this. So the model is very similar to before. The notation changes a little bit because we had to use a bit of a different non-dimensionalization, but the model is very similar. So you still have your conservation of mass equation. The control no longer appears here. That's one of the reasons why this is a bit harder. And similarly, when we were doing temperature control, it was the same. So yesterday, we'd have a control here at the right-hand side. But now, because of the way that the control acts, this doesn't happen anymore. But the equation for the flux is very similar. It's just written a bit differently, where you still have your third derivative, and your first derivative gives you the fourth derivative in a second, and then there's some other powers of h going around everywhere that give you the h cubed over 3 that you're used to. But then the control now acts a bit differently in this equation. So there's the control is going to be f, but f comes from phi d. So as I said, we have, let me go back to the diagram. We have this phi d that we can control, but then for it to get to the fluid, it has to do its thing in the air and then enter in the stresses. And so actually there's a function of phi d that's going to appear in the stresses. It's not going to be phi d directly. So f here is the resulting control from phi d, but that appears from solving a second order PDE on f with the right-hand side phi d. So phi d appears as a right-hand side on an extra equation on our model. That extra equation you solve for f, and then f is the control that appears here. I don't think I defined d, but d is the height of the domain. So because now I have two plates, so d is the distance between this plate and this plate.
Susana,
Yes.
is the electric susceptibility non-constant then? Is the is this
Yes.
is that the electric susceptibility of the dielectric?
And we just treat it as an applied voltage.
Yeah.
Constant on specific strips, say. You
Yeah.
can change the values pretty
But
quickly.
it's not just confined, so the electric forcing isn't just confined to the interface.
It is in the context of a perfect conductor
Yeah.
migrating there,
Yeah.
but then you solve the Laplace equation in the perfect dielectric region.
Yeah, so to get here, yeah, this is the part that I didn't do much. To get to this equation, you solve Laplace's equation between here and the interface. And then that gives you the interfacial stresses that then you plug into the other equations.
Okay.
So that's where you get this f from. Yes.
Because in the perfect conductor, it's non-constant.
Which is zero. In this paper.
Yeah. So yeah, so
So in the lower fluid,
yeah, which is air.
so is the electric forcing throughout the fluid, or just at the interface?
Yeah,
Just
so
at
the
the
voltage is 0 here and at the fluid, and then you apply voltage here, that then affects the interface.
But it's not throughout.
No.
So why is, when you go to the weighted forcing equation,
Yes.
is the forcing that F?
Yeah.
So how does it come into the, oh, but that's not, okay.
Yeah, so you get this f by solving the Laplace's equation
And
here.
applying the interfacial
Yes.
stress condition.
Yeah, so then it appears at the interfacial stress,
But in the
and that's how it
original
gets.
equations, it's only in the
Yeah.
interfacial. Okay.
Yeah, exactly. Yeah, so that's why, yeah, we solve it here, and then it just appears here from
Yeah.
the interfacial stresses. So that's why it's a bit harder to do, because you're not really forcing the fluid, right? You're forcing what's happening outside the fluid, so that it does. Okay, so we didn't even try because we knew it wasn't going to work. So you could try and do something like h minus 1 or flat or whatever here, but then this would sort of influence this equation, but it wouldn't do the right things here because it's not influencing h directly, it's influencing flux. And so we didn't even have hope that proportional or feedback controls would work for this. It would be way too complicated. So for this reason, we went directly to an optimal control setting. So the idea is similar to what we've done yesterday. So we get a target state capital H, and we want to minimize this cost functional, which says exactly the same as before. You want to be as close as possible to capital H for all times, and you also want to minimize the cost of the control. So you want to minimize the effort that you're putting in your controls. Now, we chose this form of the cost functional because it's the most common one. And we like things to be quadratic because we can differentiate them and everything. It might be more realistic, and we might look into that in the future, to use a different cost for the control, because maybe what you want is that it doesn't vary too much from one time to the other, so you would consider total variation, or you don't want its derivative, like you don't want very sharp changes and things like that. But for now, we just tried this one because we know how to deal with this, and then we're going to make it harder. This was already hard enough. And so like yesterday, we had, when we were doing LQR, I had the cost that sort of looked like this, and then I constrained it to solve the differential equations. We're going to do the same. It's going to be constrained to solving the equations that I showed you in the previous slide. Yeah, and the other difference is that now we're also integrating space and time, because our functions are PDEs now, not ODEs, and that makes everything a bit more complicated. So just for notation for the next slide, I'm just going to say the first, like, we can rewrite the PDEs as saying the time derivative of age is some function of the control, the flux, and the height. The time derivative of the flux is a function of everything, and the third equation didn't have a time derivative, so it's the same function equal to 0. So we're minimizing this cost function, constrained with the solution solving these 3 weeks. Okay, and so the idea is exactly the same as before. You don't like constrained problems, you make them an unconstrained problem by introducing Lagrange multipliers or adjoint variables that then transform these 3 constraints into extra terms in the cost functional. That's what we do here. We introduce 3 Lagrange multipliers, one for H, one for Q, and one for control F. We call them either adjoint variables or Lagrange multipliers. In PDE, constrained optimal control, we usually call them adjoint. And so you then go and minimize this whole thing instead of the previous term. There you go. So similarly to before, you want to take then derivatives or variations, because we're in a functional analysis setting. You then take variations of this big function with respect to the 3 things that we care about: the height, the flux, and the phi d, the control. Actually, take variations with respect to f as well. And this gives us, with some abuse of notation, the equations that we need. So, as I said, if you take variations with respect to height, flux, and f, with Lagrange multipliers for each of them, you get the state equations. So if you go here and you take derivatives with respect to lambda f, you get this, and then if you get derivative with respect to lambda q, you get this, etc. So this is known. But then the interesting thing is to take the variations with respect to the other things. So you take variations with respect to h, q, and f, so they're like derivatives, and you get the adjoint equations, which is what we need to solve. I'll show them in the next slide. And then if you take the derivative with respect to the control itself, that gives you a descent direction that you can do optimization. So let me make this a bit more clear. So if you go onto this massive thing, and you take a derivative with respect to h, for example, there's an h here, which is like an h minus capital H squared, so this gives you a 2h. There's an ht here, so you integrate by parts and you get a derivative of this guy in time, and then there's going to be h's in all these functions, fq and ff. So the equation for the lambda h is this massive horrible thing here, but it's linear on all the Lagrange multipliers. So there's a q squared here, but we, in this setting, and I'll explain why in a second, we assume we already know q and h, so they're like some coefficients. So this is linear in all the lambdas. That's why I colored the lambdas there. And then you do the same for the derivatives with respect to q and derivatives with respect to f, and that gives you these equations here. So the for the Lagrange multiplier on Q, you get a linear equation of this thing, then for the Lagrange multiplier on F, you get an equation. It's not really important what these equations look like. You can sort of get them using Maple or something. I think the main point here is A, they are linear on the things we're solving for, and B, they're all backwards in time. Because you integrate by parts to get the derivative and you get a minus sign. And then when you get the derivative with respect to the control, you get what we call a descent direction. So that's sort of telling you that to update your control, you need to go to take the previous one and add the lambda f that you get from the third equation. And this is sort of what you need. So here's what you do in practice. So you start with your initial guess for phi d. It can be anything. And then you solve your PDEs forward. So you solve your PDEs in time as you would if you just had, I'm going to try this forcing. That gives you an h, a q, and an f as a function of space and time for all your time period. And then you, so this is the equation to solve, just to remind you. You solve this forward. And then once you have h, q, and f, you then solve the adjoint equations backwards in time. And that gives you your lambda q, your lambda h, and your lambda f. And from that lambda f, you then plug that into the phi d equation here, and that gives you a new phi d. And you sort of know that it's like doing gradient descent. So your gradient of that big massive function that I introduced with respect to the control is this. So you know that if you go in the direction of the minus gradient, you should do better. And then you do gradient descent on this. It's just a massive, complicated gradient descent. So you go in this direction. You need to do clever things to find out how big of a step you do. So usually you know that you go in the direction of the gradient, but you can go, do I just add the gradient? Do I add 0.1? Do I add 0.5? And normally if you're solving for a normal optimization problem with a function that's not too complicated, you just evaluate your function at like 10 points. And then you pick the better one or the best one. But in this case, you would have to solve your PDE in like 10 points or 1,000 points, whatever. So there's clever things you can do to minimize the number of PDE solves to do this well. And then you repeat this until you converge. And what converge means, you can say, you can see what that is. But yeah, you look at your cost functional and how it varies, and when it's not varying too much, you assume it converged. So how does it work in practice? So we are going to be trying to control this to something that looks like this, because we wanted to hit it until it breaks, and so we want to think to something that looks like it has a corner to see if this would work. And actually, it does work very well. So very quickly, you converge to an interface shape that is close enough to what you want. Of course, there are some differences here in where the corners are, but this is not too bad if you're trying to do something like this. So this is just for the weighted residuals model, and this is a plot just to show sort of how this works. So on the left, I'm just plotting the interface over time, just to show that we have the shape that we sort of wanted. On the right, this is the control. I mean, this is not saying much, but the control is actually varying a lot in space, but that's okay. It's also not too big, the variations that we get. And the plot in the middle is basically plotting how far we are from the target. So for most of the time, like our difference between the desired height and the current height is actually pretty small. What I'm showing here, and that's one of the reasons I have this plot, this is something that happens a lot when you're doing optimal control with a finite time. Because in your cost, you have the cost of being too far from the desired solution and the cost of the control. And usually what happens when you're just doing straight up optimal control in something like this is that because your optimizer knows that you're going to stop your problem at t equals 150, for example, it says, oh, actually, it's a bit cheaper for me to switch off the controls, 5 time steps before I end, and let the interface deviate a little bit, because I'm paying to keep controls on. And so it's very common to have this in optimal control. It's called the turn-back effect, where towards the end, the controller just decides to switch off. Yes?
The 5D
Yeah.
has all these oscillations.
Yeah.
Is that the number of unstable nodes in the system?
I don't know, actually. We didn't check. Well, it might be. I think we should look at, I don't know if I have a plot for this. I'll check. Because in this case, we're trying to control to this. So it might be that just there's weird things happening at the kinks.
Yeah,
But if we,
it's
yeah.
interesting, you have these, it's like a sine wave of
Yeah.
a certain period, right?
Yeah.
And the period is much smaller than the domain.
Yeah.
So you could be
Yeah.
trying to kill the unstable nodes.
Yeah. I'll see. I think if we look at the solution for the stabilizing the flat solution, it might be easier to see that. I don't think I have a plot of that in here, but we probably have it somewhere and I can look at it.
You have a better memory than I do, but I remember Alex noticed when we were experimenting early on that the mechanism it was finding was rather than doing it all via the distant field, it was stabilizing it up to the point where surface tension can take over. So
Yeah.
it was shifting the number of unstable nodes quite strategically in a way where you do part of the work via the input voltage and part of the work surface tension takes over laterally.
Yeah.
But I think that's a good point.
Yeah.
So does the control actually give you information about the physics going on?
Yeah, we think so. Like it does learn it. That's why the optimization is so good. And the next thing that I'll do is actually slightly better, and I'll explain why when I get there. But yeah, so this is actually good, but yeah, it's sort of, you're giving your control sort of the ability to predict the future when you're doing it, because you're doing it from the beginning till the end. And because of that, it sort of does see what applying that control does to the system, and then it comes back into something better. But yeah, I'll check if we have plots of the zero solution, and if not, we can ask Alex next week, because he'll be here, and I'm sure he'd be interested to look at that. But yeah, so a big thing in control, and that actually motivated some of the things we'll do next, is how to stop this from happening, and people know how to stop this from happening. Very hard in a second. Okay, and then we did the thing that I advertised. We took these controls, we put them in DNS, and obviously it worked for a bit, and then it doesn't. So you wanted to have the blue shape, which is what the model is doing, and the DNS, the black wavy shape that is doing horrible things. Alex likes to call this a disaster. I'll just use these slides. So what do we do instead? So what we do instead is, and I think this is the main new thing that we came up with for this problem, is we use something called model predictive control. So this is the thing that's well known in the optimal control theory that I was talking about earlier, that people used to, first of all, stop that turnpike thing from happening, but also to introduce some sort of feedback into these models. So model predictive control is how you introduce feedback in an optimal control problem like this. And so what does this do? So this plays with the idea of predicting the future. I was going to put a picture of this book somewhere here, and I forgot, but this is one of the nicest books for nonlinear model predictive control, which is good for PDEs. But the basic idea is as follows. So you start at some time t equals 0, and then you solve your optimal control problem for, say, I don't know, 10 or capital TH. So you solve it for that time, which is probably, you can solve it until the end of time, but you can use it to make it faster. You can make this shorter than all the time that you want to solve a problem for. And then you take the control from this optimal control problem, and you apply that control for a small time, say 1. So you apply your control from t to t plus 1. And you solve it from t to t plus 10. And then what these models do is you compare the output of this control to the thing you predicted when you first solved for the optimal control problem. And then you solve it again. So you start again at t plus 1, and then you solve it again for the same interval. So you start with a very big time interval. So say you want to solve it from here to here. Then you solve it from here to here. Let's call it t plus th. And then you stop here, you see what your model is doing, and then you start again. And then you do it again and again. And you do this until you cover the whole interval. And this, I mean, if you have a perfect model, obviously you don't need to do this. But if you have a model that has errors, or if numerical errors are bad, or if you want to solve it, like if you have a model that's very expensive, you want to solve it with a cheaper numerical solver or something, basically what happens is that if your optimal control was predicting things would happen like this, but then you have something worse, like, I don't know, you do what you're supposed to do at the beginning, but then you do this, then this will create an error, and this error will build up. That's what was happening when we were putting in DNS. And so when you're too far, you start again. So that's the idea of model predictive control, and people have been doing this for ages, but not for PDEs a lot. PDEs is recent, and then you repeat this until everything is covered. And yeah, there are several advantages to do this that I don't have time to cover. So this is what people usually do. And what we decided to do in our problem was, okay, let's do the same. Let's solve the optimal control for the weighted residuals model, and then apply the control to the DNS. And then instead of deciding we're going to do TT plus 1 or something like that, we said, okay, there's a model error that can be big between the DNS and the model. Whenever the difference between what we predict with the model and what the DNS is doing is big enough, and big enough is whatever we want it to be, we solve the optimization problem again. And the advantage of this is because you already have the previous solution, we already have a pretty good guess of what the control is going to be. So the optimization mechanism is not going to be very hard. Like, you don't have to do a lot of iterations because you already have a very good first guess. So yes, just to summarize what we're doing, what we would really, really like to do is control the DNS of Navier-Stokes equations. What we can do is we can control the weighted residuals model. And so we start by controlling the weighted residuals model. We take the controls, we put them in the DNS. Whenever the DNS is not behaving like we want it to behave, we solve the optimal control again with a very good initial guess. How many slides do I have left? I'm going to finish it. Okay. So here's what it looks like. So again, we want to control to this red shape. This is what the DNS is going to be doing. And we are going to recompute the control for this figure whenever the DNS is far from the weighted residuals by more than 10 to the minus 4. This is like overdoing it, but this was like the first thing we tried to see if it worked, and basically it does work. And it works really nicely. So it almost works better than the weighted residuals result that I showed you earlier. There were much more differences around here than there are now, which is really nice. And yeah, as we said, like all the computational cost is in DNS. But then all the computational cost of the optimization is in the first time that we optimize. Because then when we optimize every time this happens, we can actually do it very cheaply because we have a good first guess. So this is what the same plot as before, where again, so this is what I think what we mean by uncontrolled is actually if we just apply the optimal controls and put them into DNS without thinking. Again, just like what I showed you yesterday, it starts working, but then suddenly it goes away and it goes back to some other solution. And then the other two curves are if we repeat the optimization every time we go more than 0.1 away from between the DNS and the model. We repeat the optimization much less often, but we can still sort of stay pretty close to it. But then if we do, again, 10 to the minus 2, we're already doing pretty well. But we are re-optimizing. Like each symbol here is when we start an optimization again. In this one, we only have like 2 or 3. In this one, we have lots. But they're really quick. And the nice thing about this is that the optimization can be done within 1 or 2 time steps of the DNS. And so it can be done efficiently when compared to the DNS. Obviously, if we're applying this to a real thing, we need to do it faster. but the optimization is pretty weak. And this is a slide with same results, with a similar results as before. So in here, we're trying to control to a flat solution or to the hat-like solution that I showed before, or to a Warwick W, because we were in Warwick. And Strathclyde that Alex was from didn't have a nice shape that we could optimize to. And we could pretty much do it for any shape, really. And again, so this was, I can't remember how many times we recomputed here, well, with 10 to the minus 2. But even for the flat solution, we didn't have to recompute a lot. And for the others, we did because the solutions are much less regular. So if we were trying for shapes that are a bit more normal or nice, then this wouldn't happen. We would have something more like this. But it's nice to see that we can pretty much put any shape that we could think of with kinks and derivatives that don't exist, and it still works pretty well. Okay, so I thought I would talk for an hour, and I'm going to talk for like 40 minutes, but I think we'll be fine. I think we can have coffee. So just to conclude on this part, so we spent a lot of time, and I spent the best part of the last, 10 years looking at linear control things. And linear control is really good, and it works, as we showed, hopefully. I think if we convince you of anything, is that linear control works for cases where you don't even think it will. It is really good, but sometimes it's not a viable option. In this case, I don't think we would have been able to control this problem using just proportional controls like we were using yesterday. But then what we can do is, okay, we have a very good model, and we cooked up the hardest case to control that we could think of at the time, which is like already below the plate so that it's already unstable and with more things going on. And then you can optimize this model with optimal control, even though you can't or you shouldn't do it with linear proportional controls. But you can control it to any complex state that you can think of. And unsurprisingly, this breaks down when you apply directly to the DNS. But then you can adapt other optimal control techniques like model predictive control to give you an efficient and a robust way of controlling these things. So what we're trying to do now is making things a bit more realistic. So again, in this case, we assumed we knew the solution everywhere, so we can do restricted observations like what Oscar was talking about earlier. Ideally, you would have noisy observations because in an experiment, you won't have exactly what the interface looks like. We are really trying to find out other problems that are not thin films to try and apply this for, because actually, I mean, actually having this applied in actual experiments is really hard. And even when we finally were like, oh, we think we can control this with temperature or anything, and the hard part was then how do we communicate with the experiment, right? Because usually what people that do these experiments typically do, because that's what they need to do, is there's a person there that changes the temperature or changes the voltage or something. And if this is changing every second, the person can't do this quick enough. And so we need to find a problem that we can actually communicate things, and they have the systems for well. So actually, a couple of months ago, we had somebody come to a seminar, and that actually, I think I sort of learned this, but he said it in one sentence that made a lot of sense, right? When people who do these types of, people who develop the control theory and this model predictive control and things like that, and proportional, so the words that describe this the best is the PID, it's proportional integral derivative controllers that are linear proportional controls. There's a lot of theory for this, and then when you apply this to, most of the time what you're applying this to is plant systems like factories or places where you build things. What people have is a table with constants that they know it will work. And so you go to the table, you search on the table, and you click a button in your software or whatever is controlling your machines. And that was the state of the art for proportional controls, I don't know, 10 years ago or something. And what he said now is that actually the hardware and the software improved a lot, so they can connect it to the computer and it can do this for you. So these things are starting to exist, but they don't exist yet for the types of experiments that we're doing. And so they show us there's a lot of brilliant things that they're using with these types of ideas. He showed us a lot of nice videos of people who are having treatment for strokes, where they do some sort of physical therapy based on electric shocks to their body. So they have some sensor that feels like their heart rate and what they're doing, and then they can shock them very little, right enough that they can then start gaining movement and things like that. So they can retrain their arms or like things that have been paralyzed that are being treated for. They can do that very efficiently now with things like model predictive control, which I think is very good. But yeah, so we're not health people, so we can't do that. But we're trying to search for problems where we can actually test this in the real world, and that moves slowly enough that we can do that, because I don't think the ones from today are that quick, but the simulation that I showed at the end of yesterday with the controls, I think that was 1 second of real time, wasn't it? So like that t equals 1 where I started applying the controls was 1 second in the real world, and we can't possibly make things that fast. So yeah, there's still a lot of things to do, but it's an exciting area, and I hope that I convince you that it's a nice thing to look into. And with that, I thank you about 20 minutes earlier than I should have, but I'm happy to answer any questions. Thank you. Oh, yes.
It's quite impressive how we work. And what is one clear for me is that in this control idea, we need to use some new physics involved. Because initially, once we have some things or sources along the world, it's a total original there.
Yeah.
Does this change the original problem?
Yes. And that's why we have all those errors. Like the last time I gave this talk, I don't think there's anyone here that was here the last time I gave this talk in Loughborough. There was like, they stopped me for like 10 minutes during the talk, and they were discussing the physics. And they were like, is it still compressible? Is it incompressible? Is it still this? Is there? And I'm like, I think so. But there was a very long discussion between like 3 or 4 people in the audience until they were satisfied that it should be okay. But yeah, there is. Yeah. Well, they didn't. Like I had to convince. Well, they had to convince each other that it was, because I don't know more. Yeah. Yeah. So that's one of the reasons why we wanted different control mechanisms. Like that one is really good, because that one is the only mechanism we could think of that puts the F on the right-hand side over there. Where's the model? So the only mechanism we could think of that puts an F here was the Boolean section one, which is why we like it, because this is good. Like having an F here is good because it makes it easier to control H directly. But everything else doesn't. But yeah, but we were like, that's why we started searching for other things, because it's really like it's not realistic to do this, right? And again, everything that I've done here was in a 1D interface for a 2D problem. In real life, you actually have a third dimension. And so what does it mean to have point actuators in there? Do I have still little holes? Do I have a slot? Do I have more, like, how does it? And we looked at the 3D problem for a bit. I should have included something about the 3D problem. Yeah.
Yeah, so we put them as dirichlet boundary conditions on the vertical velocity.
Yeah.
They're not delta functions because it's difficult to define them as such, but they are Gaussians with a small width.
Yeah. Yeah. So when we were doing the DNS, we were solving exactly the same problem. Yeah.
Minimize the number of, the best number of fragments. The optimum.
Yeah.
Or the optimal time step?
I think it's better probably think of it at the time step level, because if you just count the number of cells or degrees of freedom in that way, you will still have to resolve the kind of most delicate features of the flow in the same way. But this will save you tons of time. Well, first of all, you can do backwards and forwards configuration using ODEs. I think this basically limits the amount of recalculations you need to do so much that I think you gain at least a couple of orders of magnitude in computation efficiency. So if you couple this with something that has, say, adaptive net refinement and is well parallelized, I think it's close to the best you can get, depending on the method you pick. But
Yeah, but that's one of the reasons. Like we did do the physics like that, but but if we wanted to actually do an experiment, that would be really hard. Yeah, we have looked. Now I regret not having included Ruben's papers here. We did look for years of what would happen in the full 3D problem and where we should put. It's much harder because then immediately you have an infinitely larger number of places where you can put your actuators. And you have unstable eigenvalues in both directions, and you need to be really good at that. And even solving the KS equation, like the first one, which I can solve in like maybe 2 seconds in my laptop, solving it in 2D is much, much harder. And that was something that at the time I didn't even think about, but immediately got like very slow, very quickly, without us realizing when we were trying to do optimal control for that.
Versus the AI free bubble.
It had to happen. It was going to happen today,
What's
wasn't
gonna
it?
happen? Illusion. Okay. In my experience, if an industry partner came and had a problem that is amenable to the kind of things you're talking about, they would come and say, with all this data, can we use all the data and machine learn using AI, some kind of something, magic in the end. Right. What's your answer?
So I went to look at last week.
Okay.
They did care, and they threw out all of the information that we know about it. And they plugged it into like a giant reinforcement learning model with millions of nodes. And even if you were doing that, the input step is still generating nothing, even just the stairs.
Okay.
So they have to develop surrogate models to generate more bad quality data faster than the transient models. And they can still, do what but it's really hard to generate that data. And I think, I had a big chat with Mark, I think there's a lot that they can do to make it faster by using, information we have about it, but then do it with their computer scientists who don't know about it. But it's definitely possible that I start using things from things from the set of computer scientists.
Yeah.
But I think there's probably a middle ground. We just tracking things and doing it
Yeah.
but maybe
Sure. Okay. But for now, do you think that you can convince people that this is a better way to go than on it all the time?
I think so. I mean, especially I didn't see last week's stuff. I've seen similar talks about a year ago where people were trying to. They weren't doing thin films, but they were doing your usual Navier-Stokes with an obstacle in the middle and things. It wasn't too bad, but they were still solving the PDEs. Because it was better than getting the data. Like they were getting the data snapshots to try and estimate parameters in PDEs. But they were, I think they were still needing to solve the PDEs because it was
Yeah.
and even like, I don't know, how there was more experience of PD discovery. I have a master's student now trying to solve a slightly different PD, but with similar nonlinearities using a neural network. And he was like, he was like, oh, it's going to be okay. I don't know why people don't always solve PDs using neural networks. This is so intuitive and nice. And then he calls me on Monday, like we had an online meeting, and he was like, this is not working, and I don't know why. And it's because your PDE has like boundary layers, and it has, so there's still a lot, and it is sort of known, I think people have accepted now that if your PDE is not a straightforward thing, it is better to use the information you know. And even if it's in a physics-informed neural network type thing, it's better to use more things. It's not there yet where you can just discover, I think. I don't know if others will correct me, but...
We have a PhD student working on this, and for example, defining high-order derivatives is very difficult because any associated behavior and so on gets confused really quickly. So if you want to do, convection diffusion, you're golden. But as soon as you want to, say, discover something that's genuinely new or surprising, it becomes quite challenging. A, you don't know what to trust in many cases, but B, even if you do get something, you may get an array of terms that are nonlinear that you don't know what they're going for. If we have time, though, and depending since Oscar is leaving, I was going to plug Vanellis during my talk anyway. They run an AI accelerated CFD. So one of my former students, Michael, has started a company working on AI accelerated CFD, and Oscar has finished an internship there for 3 months earlier this year. So he has the intel on maybe an in-between solution, like what we asked about. But my view on it is that as long as it contains the word physics informed, it's already much more powerful than just trying to generate or throw data into one big box and hope for it.
And sometimes all you need is a funky boundary condition. You don't even sometimes do nonlinearity.
Or complicated nonlinearities or higher order derivatives. Like boundary conditions already confuse you.
Something I think that's very heartening about your approach to the robustness to uncertainty, right? Because like the big problem with the machine learning people is propagated in equals everything out, right? And ultimately, like right now, it's not just about people's abilities to do machine learning. It's that companies come to you with 7 noisy data points and want you to machine learn them, right? Whereas you can actually have some idea of what to do with it and whether you can do it.
Yeah, but there's also lots of interesting, especially like people love the chaos equation, even people who know no fluids. Because, as Dimitri said, the exhibit special chemical chaos is a really important problem that people like. Usually, people who are doing all sorts of surrogate models, neural networks, proper orthogonal decomposition, they'll do, okay, heat equation works, Berger's equation, okay, chaos. And then they're like, look, it works there too. But then when you go and see the parameters that they use, is only the high ones that don't have chaos yet. There was a lot of work coming out about, I think, 5 years ago, whenever Ruben finished his PhD and he was pseudo working with me, where were people trying to predict when chaos is going to happen, or like, because in some parameter regimes it stays in one solution and it jumps to another one, and so they were trying to learn when that's going to happen to sort of stop it. And we started doing that for a while. It didn't work very well. And then Ruben decided that it was better to go to industry or something. And he abandoned us, which was sad. But he's doing well, yeah. But there's a lot of interesting things happening, even if you're not thinking about the fluid dynamics of these problems, because they're very rich.
That was all the stuff.
No questions we can scope earlier.